The oscillating field is the common topic studying the particle physics and the field theory, and today we will talk about the Oscillon field. The Oscillon field is quite different with the ultralight scalar field. Unlike the ultralight dark matter, Oscillon field has some distinct properties, like as the first of all, the field is spatially localized, and due to the self-interaction term, like as a cortic pi 4 or cosine potential, like as a periodic action, it has a non-linear term. So even though the Oscillon field has a time periodic property due to such a non-linearity, and the spatially localization makes the different behavior. So here is the comparison between the oscillons and the ultralight dark matter. Both are time periodic oscillating field. But the oscillon field, already I mentioned, the oscillon fields are spatially localized. Unlike the URDM is nearly free, and it has a coherent wave solution in the galactic halo. And oscillon field has the non-linear self-interacting coupling term, so that this makes the stability from the cortic coupling. But the URDM is governed by the Schrödinger-Poisson equations, which describes the gravities and the quantum process, and this can make the solitonic core, like the dwarf core or the galactic halo. So the such a bound state comes from the gravitational effect, not the self-interacting coupling. And the Oscillon field has some finite lifetime, but long-lived. But the URDM is a candidate of the dark matter, so this does not decay. And such Oscillon field typically introduces as the early universe component, especially after the ratings of the inflation. So to be specific, let's consider the following potential. The self-interacting term has a negative cortic, so there is a minus sign, and so the such a minus cortic term make the flatten for the small pi. So these black lines correspond to the potentials, given potential, and this dotted line describes the pure quadratic term. So in the small pi, the potential is flattened at the pure quadratic term due to the negative cortic, but to make the stability for the largest pi, there is a pi 6 term high dimensional operator. So in the large pi, the potential is more steeper than the pure quadratic term. So the point is we adopt the additional term of the negative cortic here. This makes the flattened potential than the pure quadratic term. The equation of slow motions for these potentials is the following. Because we consider the inhomogeneous spatial field, there is also the gradient term, partial derivatives, unlike the homogeneous ultralight dark matter. The solution has the following form: the harmonious light terms with time dependence, and the amplitudes that depends on some spatial position. Here, so we did not consider the expansion effect of the universe here, so there is no Hubble prediction term now. So what is the effect of such a non-linear term, especially the negative cortic? The curvature is given by the second derivatives of the potential, and the cortic terms contribute to the curvature. For some properly large field values of the pi, the spring constant or the curvatures that are small. So the restore force, as analogy to the classical mechanics, such a restore force to the spring constant becomes a decrease when the field value pi becomes large. So the compared to the pure quadratic potential case, this potential with the negative cortic can make the largest amplitude. due to the small spring constant along the large build values of the pi. So the point is, if we adopt the negative quadratic negative quartic terms in the potential, such as sharp interacting coupling and the nonlinear term, then the curvatures or the effective mass, or we can say that the frequency is decrease, or frequency is soften when the oscillation amplitude is large. So the frequencies becomes the lower than the bare mass, and this forbidden the radiation. We cannot satisfy the radiation condition, and such no radiations impact makes the Oscillon field lives in the long time. So the logic is the following: there's a negative quartic term in the potential, and the effective frequency is softened. There's a no radiation, and as a result, the Oscillon field has a long uh, lifetime. And now I turn to the why the Oscillon field becomes localized. Uh, if we consider the following linear equation and apply the solutions of the harmonic lighting terms and the spatial dependence function, then the such uh, equation of motions reduces in the Helmholtz equation with the wave number k with the relations between the energy and the momentum. When the frequency is larger than the bare mass term, the such as partial function psi of the r has the just lighting plane waveform. But when the frequency is smaller than the bare mass term, the partial function psi has the decaying solution due to the imaginary wave number. So the partial function does not propagate over the space-time. So when the frequency is smaller than the mass, the partial functions just a decay. So it means that Oscillon field does not radiate it. So this makes the such a no radiations phenomena of the Oscillon field makes the Oscillon field is localized spatially. So there are some specific size, the radius of the Oscillon field. And in this circle, the Oscillon field value is large, and the nonlinear effects are important. But out of this circle, due to the boundary conditions at the spatial infinity, the field values of the pi are small, and we can neglect the nonlinear term. So here is some more detailed analysis in the spatial part. If we analyze the original equations of the motion and try the following solutions under this potential, the spatial function has the following form. And if we expand the such as spatial functions AR, then we can obtain the distribution through Oscillon fields over some specific distance, and the negative quartic term make the small values of the A of the R for the large distance. As a result, the solution gives a localized Oscillon field. So also there is other choice of the potential, so-called cosine potential, like as action ones. Also this gives the negative quartic term. This is the common cosine potential, and if we expanded this action like potential, then there is a negative quartic term in here. Then where the Oscillon fields appears in some specific areas, we can apply to the cosmology, partially the early universe. The points of the Oscillon fields is they had nonlinear terms in the potential. This makes the long-lived particle and the spatially localized and the time-dependent configuration. There are three such properties. And the example of the Oscillons appears in the leading after the inflation or gravitation within the early universe. Uh, uh, when the Oscillons are formed or merged, the gravitational waves can be produced, and also the axion with the cosine potential. And after the phase transitions, there is the bubble dynamics, especially also the other one. Bubble dynamics of the scalar field can make the Oscillon dynamics. So, um, so here's some specific example. After the implosion, especially the hilltop implosion, there's a plateau. The plateau potentials. This is similar to the negative Cortic terms in the potential. After the implosion, the frequencies are substance, so the effective frequencies become smaller than the bare mass term. And as a result, Oscillon fields are formed. This field is partially localized, and such Oscillon become the dominant one in the universe component. So before the radiations, there was additional matter dominant era. In his the progress is equal to 0, so because the equation of the start is equal to 0, so the decrease as I to the minus 3 with the scaling factors. Such Oscillon dominant era delay the radiation dominant under this effect on the CMB scales and distorts the observational result. And after this Oscillon dominant era, because has the finite lifetime, eventually the Oscillons are decayed to the other particle, and this makes the ratings end completely. And after this, the radiation dominant eras start. Also, the gravitational wave signal can be produced from the Oscillon formation or merger through the decay, so that we can test such Oscillon as results of the implosion. With the specific frequencies of the gravitational waves that depends on the Oscillon's core size on the mass. So if we consider some specific implosion scale, then we can estimate the Oscillon mass and also the temperatures and the radius thing. So we talk about the Oscillon field as the oscillating field, but unlike the ultralight dark matter, it has the distinct characteristic like as spatial localized and the finite lifetime. This arises from the nonlinear, spatially the negative Celtic term. So Oscillon field can be applied to the early universe, especially after the implosion. Due to the flatten potential, Oscillon field can be realized, and this makes the earlier matter dominant era before the early and back to the CMB, and we can detect this to the gravitational waves around the Oscillons that merges through the decay.